This thing. Okay. I like the smoke and the flashing lights. I'm not used to that, at least not in this context. Good afternoon. Are you all reasonably awake? Yeah. So who was born after 1981? Can you just show me your hands? Oh God. Okay. Does anybody know why 1981 is significant in the context of quantum computing? Let's see if this works. Yes, here we go. So in 1981, at MIT, Massachusetts Institute of Technology, IBM and MIT and Caltech and a whole bunch of other research institutes, universities organized a conference. And the reason to hold a conference was computers were getting increasingly faster and more performant. But the physics world was trying to get its brain around quantum physics and quantum mechanics. And the computers were basically nowhere even remotely near being able to simulate quantum mechanical systems. And at this conference, and I don't know if I have a pointer, probably not, but up on the back row, there is about here, there's a guy with a high temple. That's Richard Feynman. Richard Feynman is a key person in quantum computing. This guy here, this one. Anybody know who that is? You're all German, right? Or most of you? You should. This is Konrad Zuse. Yes, that's Konrad Zuse, the German father of computers. Of course, the real father of computing was Charles Babbage, who invented a von Neumann, mechanical von Neumann computer in 1823. But anyway, Konrad Zuse invented the first electronic computer. So these guys all met and they said, we need, actually Feynman came up with the first idea or formulated it. They said, in order to simulate quantum physics, quantum mechanics, we're going to need a computer based on the same principles. At the time, actually a few years before, in 1965, a guy called Gordon Moore. Gordon Moore was one of the founders of Fairchild Semiconductors and subsequently became CEO of Intel. You've probably heard of Intel. Gordon Moore came up with this law. Actually, it wasn't a law, it was just a projection. He said, because of the way transistors are getting smaller and smaller and smaller, and because of the way we're able to manufacture bigger and bigger chips, the number of transistors available to a single unit, whatever you want to build, microprocessor, memory, whatever, the number of transistors that you're able to use on a single die is going to double every year. And he projected that for the next 10 years. Subsequently, he revised that projection in the mid-70s to said it's going to double every 2 years. If you ask most people, they say, oh, Moore's law is every 18 months. He never said that, but anyway. This law, this Moore's law, has held for decades. It's held up to quite recently. We're now at the point where the smallest transistors we manufacture, in the order of 10 nanometers, hold around 30 atoms of silicon. And when you get down to that very low number of silicon atoms, then quantum mechanical effects dominate. The transistors don't really behave very well. They're not like a switch anymore. They're some kind of wishy-washy, fuzzy, maybe I'm on, maybe I'm off thing. And in fact, a lot of what happens in the inside a silicon chip is compensating and detecting and correcting for that uncertainty. So Moore's law is probably got a little bit more mileage in it because we can make bigger dies, but as far as feature size is concerned and the number of silicon atoms, it's quantum mechanical already. With with a traditional chip, in order to double the power, you need to double the size of the chip die. And with a quantum computer, in order to double the power, in the sense of the space of possible problems to which you can find a solution, and you notice that my hands are waving now. This is a key signal. In order to double the state space, you just need to add 1 qubit. And that's key. What does that mean? Well, if we look at 1 single qubit, the qubit is able to hold both a 1 and a 0, and actually all other possible states which are between 1 and 0 at the same time. So it's a little bit like a traditional bit. A traditional bit is either a 1 or a 0. A qubit can be 1 and 0 and everything else at the same time. It gets interesting when you have 2 qubits, because suddenly you have 4 basis states. If I go up to 3 qubits, I get 8 basis states. IBM's current largest prototype is a 50-qubit machine, and 50 qubits can hold 1.125 petastates. That's 1 with 15 zeros after it. So that's the current state of IBM's quantum computer. And these qubits are, assuming we can manipulate them and use them in a constructive, meaningful way to solve problems, that's a very large state space. However, if we go up to 275 qubits, then we have more states than there are atoms in the observable universe. I tried to look up what that 6 times 10 to the 82 actually is. There is no short form for it like peta or mega or giga. It's less than a googolplex, but more than anything else. So somewhere between 2 to the 275 and 2 to the 290 atoms in the observable universe. Interestingly, I also read that with 2 times 10 to the 45 traditional memory locations, you can represent the entire state down to the quantum mechanical level of a human being. So if ever Star Trek needs to become reality with beaming people up, that's the kind of information you're going to need to have to transfer. If we look at where traditional computing has been powerful, so a classical computer, even the classical computer which is in here, so there's a couple of billion transistors in here, and they're working at a clock frequency and they're performing instructions. And these classical computers are good at solving problems which we call polynomial problems. So given a problem with a particular size, as long as the algorithm to solve that problem is some low-level polynomial in the size of the problem, we can use classical computers quite effectively to do that. So for example, finding out if a number is a prime number, it's quite easy to do. Or multiplying 2 numbers together, or adding 2 numbers. Unfortunately, most of the interesting things in life aren't polynomial. That's also a very philosophical statement, because that kind of says, okay, so what's interesting and what's not interesting? But anyway, most of the interesting problems or most of the challenging problems aren't polynomial. Classic example is if you're a logistics company and you want to do some route planning to make sure that your fleet of postal delivery people all have the minimum length or the minimum distance that they have to walk or cycle with the minimum energy and the minimum time. Once you get past about 5 or 6 people, it becomes incomputable. You can't use classical computers to find the best solution. You can use classical computers to find an approximation. You can use them to iterate and find probably something which is quite a good solution, but not necessarily the best. So those easy problems and hard problems, we distinguish between them. The easy problems are runnable, computable on classical computers, and the hard ones aren't. We then have a class of problems we call quantum easy problems. One of the open questions in theoretical computer science is the blue ellipse the same as the red circle? We now know it isn't. We now know that there are problems which can be run on a quantum computer easily, which are impossible even for a classical computer. Simulating quantum mechanics, as Richard Feynman and the guys at MIT and IBM and Caltech back in 1981, that's something on the border where it's pretty well incomputable using classical computers, and it's really rather, and I use this word very reservedly, easy on a quantum computer. How does that actually work? So classical computer, we have bits which take on discrete values, zeros and ones. And in quantum systems, we have a state. And as long as, and this is the bit where, you know, I studied applied physics and electronics back in the day. And this is the bit where my engineer brain always goes into shutdown mode, is when I actually look at how a quantum computer is implemented with silicon, with voltages and, you know, real stuff. And then I tell people, you can put this in a superposition where the individual qubits are both 1 and 0 at the same time. And as long as you don't look at it, and by look I mean as long as you don't measure anything, it stays in superposition. Most people who've got some kind of scientific background or engineering background, that's the point where they, you know, inside them there's this part of them which is screaming, no, 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 it can't be possible. But it does actually work. And the other interesting thing is we can take multiple qubits and we can put them, we can synchronize them with each other in such a way that they are a single system. In other words, observing one part of that system causes the other part to take its definite value as well. How do we actually program them? Well, there's this way of visualizing qubits as like a sphere, like the Earth, with the value 0 being. Don't ask me to explain why the convention is that way, but the North Pole is 0 and the South Pole is 1, and any qubit is a point on the surface of the Earth, and we can use rotations and manipulations to move that point over the surface of the Earth. And as long as it's somewhere on the surface of the Earth and we haven't looked at it, then it stays there. As soon as we observe it, it's forced to either go to the North or the South Pole. With entanglement, we can link up multiple Earths and have the value of the point on one Earth dependent on the point on another Earth. Sounds all very theoretical, all very kind of abstract, but we can use that to design very, very powerful algorithms. If we look at where quantum computing is today, the holy grail of quantum computing is something called the universal fault-tolerant quantum computer. So this is a quantum computer with an arbitrary number of qubits or a large number of qubits which are error-free. Quantum computing in itself is non-deterministic. That means when I have a quantum computing program, I have to repeat it, maybe several times. Several may be 5 times, it may be 100 times, it may be 1,000 times. Because every time I measure it, there's always an uncertainty associated with what I'm going to measure. So I have to repeat it and look at the statistical distribution of what I've measured. If I've designed my algorithm correctly, and well and robustly, then I will see a very clear statistically significant result saying, okay, that's the actual answer. Real quantum computers introduce additional errors because they're physical devices. So they have an inherent physical real-world error, and that's added to this non-determinism. And that represents a kind of limit on the size of quantum computers, the quantum computers we can actually build right now. That's why we're currently in a state of something we call the NISQ era, which is the approximate quantum computer, where we have a limited number of qubits and they're noisy. Interestingly enough, there are actually quantum computer algorithms which are resistant to these inherent errors. The bigger the problem you try to solve, the less the errors influence the uncertainty in the answer. There are, of course, also a large number of very interesting algorithms where it's exactly the other way around. In other words, the bigger the problem, the worse the errors impact it. So there's no free lunches, but there are some snacks in between. There's also a type of quantum computing based on something called quantum annealing, which is a kind of a halfway house. Basically, you get superposition, but you don't get entanglement. So this scaling effect that you get with quantum entanglement isn't present. Where are we using quantum computers, or where do we expect quantum computers to be useful? Well, the first application area, it comes from the initial work in 1981. So it's chemistry, physics, chemistry, looking at molecules. And if you think about it, there are lots of application areas where simple molecules and the design of simple molecules and their topology in 3 dimensions or their binding energy become very important. Catalysts, for example, or battery electrodes. So a battery, I need to maximize the surface area of the electrode. If I can design the electrode material to have a very particular binding energy, I can influence the surface area of an electrode, drastically improve the efficiency of a battery. Or materials science, coatings, paints, self-healing coatings, for example. So if I scratch the surface, I design a lacquer which is very adhesive and very cohesive. So if I scratch it, it heals itself. That kind of thing is thinkable. And going a little bit further down the road, looking into more advanced chemistry and pharmaceuticals, obviously if you can calculate the 3-dimensional structure of a molecule and the binding energy of a molecule, then you can eliminate a lot of trial and error in drug development. Second area is the area of artificial intelligence. Artificial intelligence is a little bit further away. So the chemistry case is quite near. We expect that to happen soon. Artificial intelligence is a little bit further away. And I'll talk about that in a second. And financial services. Financial services, but also optimization, route planning, logistics, all this sort of thing. Where do we expect to be in what kind of time scale? In the area of chemistry and optimization, we expect to have something called quantum advantage. Quantum advantage is a projected time in the future where solving a problem with a quantum computer becomes financially, numerically, and from performance perspective, an absolute must. So the quantum computer overtakes the classical computer. That's quantum, that's the time of quantum advantage. And we expect quantum advantage in chemistry and simple pharmaceuticals sometime in the next 5 years. With simple chemical design, it's much closer. Machine learning is a little bit further away. And then something here called Shor's algorithm. And I'm sure some of you know what Shor's algorithm is. Anybody put your hand up if you know what Shor's algorithm is about? 1 or 2 people. Well, Shor's algorithm is the thing you say to the security services when you want them to have nightmares. So Shor's algorithm is a way to factorize numbers. Now, I said earlier, discovering if a number is a prime number is actually quite easy. Discovering the prime factors of an arbitrary number is really difficult. And a guy called Peter Shor in 1984, so 3 years after the idea of a quantum computer had been formulated, this guy came up with an algorithm which takes a combinatorial execution time. And you're all using probably online payments, right? Anybody doesn't use online payments? Okay, so you're all fallen victim as well. So if you're using online payments, you're using 1024-bit RSA. In order to crack 1024-bit RSA using the highest performance computer on the planet right now would take longer than the life of the universe. Over 13 billion years. Using Shor's algorithm and an appropriate quantum computer, it'd take around 10 minutes. That's why people are worried about Shor's algorithm. Don't worry. The gotcha, the but, is that in order to run Shor's algorithm, you're going to need hundreds of millions of qubits. Right now we have 50. So don't worry about it yet, but at some point it's going to happen. Over the last 38 years, we've developed 6 kind of meta methods for developing quantum computing algorithms. And if you look at the curve of the number of scientific papers being published on quantum computing, it's an exponential curve. So right now, every day I see 2 or 3 or 4 new papers on some key aspect of quantum computing algorithm design. It's really starting to heat up. The number of patents is really going through the roof. So we're entering a very, very active phase of algorithm design, and I expect in the next 2 to 3 years a lot more very significant, important results in this. Right now we have 6 tools to do this. I didn't put this up because I wanted people to understand it. I put it up because I wanted you to understand that some of this is very arcane. It's very involved. It's very mathematical. It's hardcore maths. Unless you know what a tensor is or a complex vector space or a computability class, then that's the kind of thing you need to understand in order to be able to design algorithms. So that's what a typical quantum computing program looks like, with the boxes and various gates. Quantum computers have their own assembly language. They have their own APIs. We're now at the stage where you can start to integrate classical or combine classical computers and classical programs with quantum programs. At some point, probably in the next 3 or 4 decades, we're going to be a little bit further and have maybe quantum computers working completely on their own. But right now we're at the stage where you need to combine quantum computers with classical computing. Just to give you a feel for this, is anybody here who doesn't drink coffee? You're missing out. So if you wanted to discover what the biochemical effect of caffeine was, then you could simulate the 3-dimensional topology of a caffeine molecule and its binding energy to determine how it interacts with, for example, human cells in the stomach. To do that, caffeine has its C8H10N3O2. To do that with a classical computer, you'd need 10 to the 48 bits. Has anybody got a feel for how much 10 to the 48 is? Okay, so the number of atoms on Earth, so all of us together combined with the entire Earth, is about 10 to the 50. So it's about 1% of the number of atoms in the Earth. So that's not going to happen soon. We don't have that kind of computing power. But you'd only need 160 qubits. And I'd say 160 qubits isn't so far away. Sucrose, need a few more. Now it gets interesting. Penicillin, you'd need 286 qubits. And that's getting into drug design, into pharmaceuticals. So imagine a quantum computer which can, within a couple of seconds, calculate the binding energy of some arbitrary molecule which you think might be very good, combined with this particular genotype at combating stage 3 malignant tumor in breast cancer, for example. So we're talking about individualized medicine. In order to make individualized medicine happen as a vision, probably quantum computers are going to be key technology. what does the thing actually look like? Has anybody seen one? Or the mock-up? They were at CeBIT, the Consumer Electronics Fair. If you get a chance to see one, come along. You'll probably find me there, and if you do find me there, then I'll let you climb all over it and make selfies with it. So we lovingly refer to it as the chandelier, because it's this sort of gold thing that hangs from the ceiling. Up at the top, it's 40 degrees above absolute zero. There is a funny fridge thing in it. You can see it on the right. There's some sort of silver stripes there. There's helium-3 is in there, and you use helium-3 and helium-4 like a refrigerator at home. And it takes about a day, half a day, for it to cool down to 15 thousandths of a degree above absolute zero. The whole thing is encased in a special metal, and it's under ultra-high vacuum. And under those circumstances, we can establish and maintain this state of coherence. Where are we now? Well, around 1981, the first Physics of Computation conference. In the intervening 38 years, there's been a lot of work on algorithm design and demonstrating and investigating how we can actually use quantum computers effectively. Since 2016, IBM has made quantum computers available. They're free, and we publish all our performance results. So if anybody's interested, I can show you, or you can ask me, or you can go on our website and just enroll and use a quantum computer. It's really quite easy. And the market is heating up. And we expect within the next 2 to 3 years that really our competitors are also going to come up with commercially available offerings. And the link to the Consumer Electronics Fair, yes, so 3 weeks ago or 4 weeks ago, we announced the first commercially available quantum computer. So everything up to now is all research, but now we're moving into the very first stages of commercialization. So I think with that, I'm out of time. I have another 200 foils on the details of the HHL algorithm if anybody wants to know. Thank you for your attention, and I hope you get involved. Thanks.